Welcome to the first part of our applied chemistry series, focusing on water. Water plays a crucial role in chemistry, particularly in industries, daily life, and scientific processes. In this section, we will explore various aspects of water, including its specifications, analysis, and treatment processes. Let's dive into the science behind this vital resource. We will cover a variety of topics in this video, from specifications of water to Calgon treatment. Let's dive in water. Water quality specifications vary depending on its intended use, whether it's for drinking, domestic, industrial, or agricultural purposes. It's crucial to assess water based on physical, chemical, and biological characteristics to ensure that it meets the required standards for its specific application. Let's take a closer look at the physical specifications of water, which are especially important when considering water for drinking or domestic use. Color. Pure water should be colorless. Any change in color may signal contamination, such as a reddish tint indicating the presence of iron. Odor and taste. Water should be free of detectable odors or tastes. The presence of compounds like sulfur or chlorine can alter its smell or flavor, which should be addressed during treatment. Turbidity. This refers to the clarity of water. High turbidity means more suspended particles, which can harbor harmful bacteria. For drinking water, turbidity levels should be below 1 NTU, ensuring it is safe and clear. Temperature. Water temperature also matters, as it affects its chemistry. For potable water, an ideal range is 5 to 15 degrees Celsius, which helps maintain biological processes and chemistry. Now, let's talk about the chemical specifications of water. These specifications help ensure that water is chemically safe for use. pH levels measure the acidity or alkalinity of water. A neutral pH of 7 is ideal, but acceptable ranges for drinking water are between 6.5 and 8.5. Total dissolved solids, TDS, refers to the concentration of minerals, salts, and organic substances dissolved in water. Water with a TDS below 500 ppm is considered good for drinking, while higher levels can affect taste. Hardness is caused by dissolved calcium and magnesium ions, and can lead to scaling in pipes or appliances if too high. Water with hardness exceeding 200 ppm is considered hard. Chloride and sulfate content should be monitored to prevent corrosion. Chloride levels should remain below 250 ppm, while sulfate should not exceed 500 ppm. Lastly, water's biological specifications are critical for ensuring it is safe for consumption and use. Bacterial content. Water should be free of harmful pathogens, especially coliform bacteria like E. coli, which indicate contamination by human or animal waste. Algae and microorganisms. In water bodies with excess nutrients, algae and microorganisms may grow, leading to potential health risks through waterborne diseases. Regular monitoring and treatment can prevent these risks. Let's move on to water analysis, starting with alkalinity. Alkalinity measures water's ability to neutralize acids, which is essential in various processes like corrosion control and maintaining pH stability in natural water systems. Sources of alkalinity. Alkalinity primarily comes from limestone and other carbonate-rich geological formations. It is measured in milligrams per liter of CaCO3. For potable water, the acceptable range is 20 to 200 mg/L. Types of alkalinity. These include bicarbonate alkalinity, found in water with a pH between 4.5 and 8.3, carbonate alkalinity for pH between 8.3 and 10, and hydroxide alkalinity for water with pH levels above 10. The determination of alkalinity is carried out by titration, where we add a strong acid like sulfuric or hydrochloric acid to the water sample until it reaches a pH of 4.5. A pH indicator like methyl orange helps identify the endpoint of this reaction. High alkalinity in water can be beneficial as it helps resist pH changes, which is crucial in various industrial applications, including boiler systems. However, it needs to be controlled in specific contexts to prevent corrosion. Now, let's turn to water hardness, a common issue in water chemistry. Hardness is caused by the presence of calcium and magnesium ions, which affect water's suitability for domestic and industrial use. There are two types of hardness. Temporary hardness, which is caused by bicarbonates of calcium and magnesium and can be removed by boiling the water. Permanent hardness, caused by chlorides and sulfates of calcium and magnesium, which cannot be removed by boiling and require chemical treatment. The EDTA method is widely used to determine water hardness. This process involves complex symmetric titration, where EDTA, a chelating agent, binds with calcium and magnesium ions to form stable complexes. In this procedure, we add a few drops of Areochrome black tea indicator to the water sample. In the presence of calcium and magnesium, the solution appears wine red. We then titrate the sample with EDTA, and as EDTA binds with these metal ions, the color changes from wine red to blue, indicating that all hardness ions have reacted. When we talk about potable water, we mean water that is safe for human consumption. This type of water must be free of harmful microorganisms, chemicals, and toxins, and must have acceptable taste, odor, and appearance. The World Health Organization, WHO, and various national health organizations have strict standards for potable water to ensure that it is safe for daily use. The key criteria for potable water include bacteriological safety, meaning no presence of pathogenic organisms. Chemical composition, which must be free of toxic substances like lead, arsenic, and nitrates. Physical properties, ensuring that water is clear, colorless, and free from unpleasant taste or smell. When it comes to domestic use, water must undergo various treatment processes to ensure it is safe, clean, and suitable for human consumption. Let's go through some of the key steps in the treatment of water for domestic purposes. Coagulation and flocculation. This is where chemicals, like alum, are added to water. These chemicals cause the fine suspended particles in the water to clump together, forming larger particles known as flocks. These flocks are easier to remove. Sedimentation. After coagulation, the water is allowed to sit, giving these flocks time to settle at the bottom of the tank. This process clears the water of larger particles. Filtration. After sedimentation, the water passes through filters like sand filters to remove smaller particles that weren't captured earlier. Disinfection. Finally, disinfectants like chlorine are added to kill any remaining pathogens. Other disinfection methods, such as UV or ozone treatments, may also be used. In areas where water hardness is a concern, methods like ion exchange or reverse osmosis are used to soften the water. Let's now discuss the lime soda process, a widely used chemical method for softening hard water. This process is primarily used to remove both temporary and permanent hardness from water by adding lime and soda ash. The lime precipitates out calcium bicarbonate, while the soda ash removes magnesium by forming insoluble compounds. This method is particularly useful for large-scale water treatment because it is economical and highly effective at removing both types of hardness. However, it does produce a large amount of sludge, which can be a challenge to dispose of properly. Despite its effectiveness, it may not completely remove all magnesium hardness. Next, we have the ion exchange method, one of the most efficient methods for water softening. The basic principle here is that undesirable ions in the water, like calcium and magnesium, are exchanged with more desirable ions, usually sodium, contained in a special ion exchange resin. There are two main types of resins used: cation exchange resins, which attract and hold positively charged ions, like calcium and magnesium; anion exchange resins, which remove negatively charged ions, such as chlorides or sulfates. This process effectively softens water by removing hardness-causing ions, making it highly suitable for domestic, industrial, and boiler feed water applications. Let's go deeper into the ion exchange process. In this process, hard water flows through a column filled with cation exchange resin. As the water moves through the resin, calcium and magnesium ions are exchanged for sodium ions, effectively softening the water. But this resin doesn't last forever. It gets saturated with the hardness ions over time. When that happens, it must undergo regeneration. This is done by flushing the resin with a concentrated solution of sodium chloride and ACl. The sodium ions in the salt solution displace the calcium and magnesium ions, replenishing the resin, so it can continue softening water effectively. Let's review the advantages and disadvantages of the ion exchange method. Advantages: highly efficient. The ion exchange method removes both temporary and permanent hardness from water. Immediate results: it provides soft water instantly, without lengthy processes. Compact design. Ion exchange systems can be designed for residential use, as they are compact and efficient. Disadvantages: cost. The initial cost of setting up an ion exchange system can be higher than traditional methods. Sodium levels. This method increases sodium levels in the treated water, which can be a concern for individuals on low-sodium diets. Regeneration waste. The regeneration process produces waste brine, which must be disposed of properly. Next, let's look at boiler feed water. Boilers require specific water quality standards to ensure efficient operation and prevent damage to the system. The key specifications for boiler feed water include: hardness should be minimal to prevent scale formation. Typically, the hardness level should be kept below 0.5 ppm. Alkalinity. Alkalinity must be controlled to prevent caustic embrittlement. The recommended range is 100 to 200 ppm. Dissolved gases. Both oxygen and carbon dioxide must be minimized to avoid corrosion. Oxygen levels should be below 0.007 ppm to prevent oxidation, and carbon dioxide should also be controlled to avoid carbonic acid formation. These strict standards help maintain the efficiency and longevity of boiler systems, preventing costly downtime and repairs. To ensure that boiler feed water meets these standards, several treatment processes are employed. Deaeration. This process removes dissolved gases, particularly oxygen and carbon dioxide, from water. Deaeration typically involves heating water and exposing it to steam, which forces the gases out. Softening. Boiler feed water needs to be softened to remove hardness-causing ions like calcium and magnesium. This can be done using the ion exchange method or lime soda processes. Chemical treatment. Chemicals such as phosphates are added to the water to react with hardness ions, forming a sludge that can be easily removed during the blowdown process. Boilers are prone to a number of problems if water quality is not properly managed. One of the most common issues is scale formation. Scale forms when hardness ions like calcium and magnesium precipitate out of the water at high temperatures, forming hard deposits on the heat transfer surfaces of the boiler. Consequences of scale formation include reduced heat transfer efficiency, increased fuel consumption, and potential overheating or failure of boiler components. To prevent scale formation, regular blowdown procedures should be conducted, where concentrated water is drained from the boiler. Additionally, water softening and chemical treatment with antiscalants can be used to control hardness levels and prevent scale buildup. Another common problem in boilers is sludge formation. Sludge forms when impurities like iron oxides, silica, and other particles accumulate at the bottom of the boiler. Consequences of sludge include reduced boiler efficiency, and if not removed, it can block valves and cause operational failures. To prevent sludge formation, regular blowdown procedures are critical, and proper treatment of the feed water, including the use of dispersants, helps keep sludge particles in suspension, making them easier to remove. Lastly, let's discuss priming and foaming, two phenomena that can cause serious operational problems in boilers. Priming occurs when steam bubbles carry water droplets into the steam system, leading to wet steam. This can damage downstream equipment like turbines. Foaming, on the other hand, is caused by dissolved solids or surfactants in the water, which creates stable bubbles. Both issues can lead to the carryover of water with steam, reducing efficiency and potentially damaging equipment. To prevent priming and foaming, it's crucial to maintain appropriate water levels, control the water chemistry, and use anti-foaming agents when necessary. Next up is the issue of caustic embrittlement, a specific type of corrosion caused by high concentrations of sodium hydroxide, NaOH, in boiler water. This phenomenon leads to stress corrosion cracking in the metal components of the boiler. Consequences of caustic embrittlement include a reduction in the structural integrity of boiler parts, making them prone to leaks and failures. To prevent caustic embrittlement, it's essential to control the use of sodium carbonate in water conditioning, as well as perform regular blowdown procedures to maintain alkalinity levels within safe ranges. Substituting sodium hydroxide with more appropriate conditioning chemicals also reduces the risk of this issue. Boiler corrosion is another serious issue that arises due to the presence of dissolved gases like oxygen and carbon dioxide in the feed water. These gases react with the metal surfaces of the boiler, leading to the deterioration of key components. Consequences of corrosion include reduced boiler lifespan, efficiency losses, and the need for frequent maintenance to repair leaks and other damage. To prevent corrosion, several methods are used. Oxygen scavengers like sodium sulfite are added to the water to react with and remove oxygen. Deaeration helps remove dissolved gases from feed water before they can cause damage. Maintaining neutral or slightly alkaline pH levels helps minimize acidic corrosion. Preventing boiler issues like scale formation, sludge buildup, priming, foaming, and corrosion is crucial for efficient operation. Several strategies can be implemented to minimize these risks. Regular monitoring. It's important to continuously monitor key water quality parameters, including hardness, alkalinity, and pH levels, to ensure the water stays within the optimal range. Blowdown procedures. Regularly removing concentrated impurities through blowdown keeps the water clean and helps prevent buildup of solids. Chemical treatment. The use of appropriate chemicals, such as oxygen scavengers, phosphates, and anti-foaming agents, ensures that water remains free from harmful contaminants and is well-conditioned for use in the boiler. Equipment maintenance. Routine inspections of the boiler system help identify potential problems early, reducing downtime and preventing costly repairs. Training personnel. Operators need to be trained in monitoring and maintaining water quality, ensuring that best practices are followed consistently. Now, let's look at the removal of silica from water, which is essential to prevent scaling in boilers and industrial systems. Silica is present naturally in many water sources, particularly where it comes into contact with quartz and other silicate minerals. If not removed, silica can combine with other hardness ions like calcium and magnesium at high temperatures, leading to the formation of hard, glass-like scales that can significantly reduce boiler efficiency. Silica scaling is especially problematic in high-pressure boilers, where temperature and pressure cause these compounds to precipitate out more readily. There are several methods used to remove silica from water. Precipitation and sedimentation. In this method, chemicals like calcium chloride or magnesium hydroxide are added to the water. These react with silica to form insoluble compounds, which can then be removed through sedimentation. Filtration. Sand filters, microfiltration, and ultrafiltration can all be used to remove suspended silica particles effectively. Advanced filtration techniques target smaller particles, improving the overall purity of the water. Ion exchange. Although primarily used for softening, ion exchange resins can also help reduce silica levels. However, they are not as efficient as other methods. Reverse osmosis. RO-RO systems are very effective at removing silica and other dissolved solids. These systems work by forcing water through a semi-permeable membrane, which blocks silica and other contaminants. Dissolved gases, such as oxygen and carbon dioxide, must be removed from boiler feed water to prevent corrosion. The presence of oxygen leads to oxidation of boiler metals, while carbon dioxide reacts with water to form carbonic acid, H2CO3, increasing the acidity and accelerating corrosion. Several methods are used for removing dissolved gases. Deaeration, a process that heats water and exposes it to steam or reduces pressure to allow dissolved gases to escape. There are two main types of deaerators. Tray deaerators. Water is distributed over trays where it meets steam, promoting gas removal. Spray deaerators. Water is sprayed into a steam chamber, ensuring rapid and effective removal of gases. Chemical treatment. Oxygen scavengers, such as sodium sulfite or hydrazine, are added to water. These chemicals react with oxygen to prevent it from causing corrosion. Vacuum degassing. This method involves reducing pressure below atmospheric levels, which forces gases to escape from the water. Let's move on to carbonate and phosphate conditioning, which are methods used to adjust the water chemistry in boilers and prevent corrosion and scaling. Carbonate conditioning involves the use of sodium bicarbonate and sodium carbonate to adjust the alkalinity of boiler water. Proper alkalinity levels help prevent corrosion by stabilizing pH levels. Additionally, carbonate ions react with calcium and magnesium ions to form insoluble precipitates, which are then removed during blowdown. Phosphate conditioning plays a key role in scaling control and pH regulation in boiler systems. When sodium phosphate is added to water, it reacts with calcium and magnesium ions, forming soluble complexes that prevent the formation of hard scale deposits. The benefits of phosphate conditioning include scaling prevention. By binding to hardness ions, phosphate prevents the formation of scale on boiler surfaces. pH control. Phosphate helps maintain an optimal pH range, reducing the risk of acidic or alkaline corrosion. The careful application of phosphate conditioning ensures that boiler systems remain efficient, avoiding the energy losses and maintenance costs associated with scale buildup. Next, we have colloidal conditioning, another important method for maintaining water quality in boiler systems. In this process, colloidal materials, substances that are finely dispersed throughout a solution, are added to the water. These colloidal agents help keep impurities in suspension, preventing them from settling and forming deposits on boiler surfaces. Types of colloidal agents. Two commonly used agents are colloidal silica and synthetic polymers. These substances act as stabilizers, preventing impurities from forming solid deposits. The benefits of colloidal conditioning include improved operational efficiency and the prevention of scaling, both of which contribute to a longer boiler lifespan and more consistent performance. Lastly, we have the Calgon treatment, which is designed to prevent scaling by sequestering hardness ions such as calcium and magnesium, keeping them in solution rather than allowing them to form scale. Mechanism of action. When Calgon, which is a water-softening agent, is added to water, it reacts with calcium and magnesium ions, forming stable, soluble complexes. This prevents the ions from precipitating out of the water and causing scale buildup in pipes and boilers. The benefits of Calgon treatment include effective scale prevention. By keeping hardness ions in solution, Calgon minimizes the risk of scaling. Ease of use. It can be easily integrated into existing water treatment systems. Compatibility. Calgon works well with other chemicals used in water treatment, enhancing the overall quality of the water. We've reached the end of our detailed exploration of water in applied chemistry. Throughout this video, we've covered critical topics. Water is a complex and vital resource in many chemical and industrial processes, and managing its quality is key to ensuring the success of these systems. I hope this video has provided you with a solid foundation in understanding the chemistry of water. Thank you for watching, and don't forget to subscribe for more tutorials on applied chemistry and other exciting topics.